Hello, everyone. I'm Christopher Januzzi, Executive Director and CEO of the Electrochemical Society, coming to you live from ECS headquarters, Studio A in beautiful Pennington, New Jersey. And it is my great privilege to welcome you to Day 3 of PRiME 2020 and this year's Electrochemical Energy Summit. Before we begin our formal program, I would like to make just a few brief announcements. First, for those of you who missed any of the live events held earlier this week, I hope you take a moment to enjoy the replays of these, available now in the online PRiME program. Also, tonight's event will feature a panel discussion with questions from the audience. You may submit your questions at any time during tonight's presentation using the QA feature, and we will direct these to the panelists to address during the session. Also, be sure to browse the question list to up-like those questions others have submitted and to see which ones you would like answered next. Lastly, I would like to take a moment to thank the many wonderful organizations without whose generous support PRiME 2020 would simply not be possible. So please join me in showing our deepest appreciation to our sponsors, beginning with our Platinum meeting sponsor, SK Innovation, our Gold meeting sponsor, Samsung SDI, Silver meeting sponsors, Ion Power Inc., LG Chem, and Scribner. Our Bronze meeting sponsor, the National Tsinghua University Department of Material Science and Engineering in Taiwan, and our contributing meeting sponsor, MDPI. Tonight, we are proud to bring you the 2020 Electrochemical Energy Summit, or E2S as we call it. Begun in 2011 as the brainchild of past ECS presidents John Aletti and Christina Bach, E2S has become a fixture at PRiME and ECS fall meetings ever since. And each year, the summit serves as a forum to bring together policymakers and researchers to explore critical issues of energy needs and the pivotal research in the electrochemical energy field to address the myriad grand challenges facing humanity today. Tonight, we continue that tradition by addressing one of the most important of these challenges, the electrification of transportation. To help us unpack this complicated topic, we have assembled an esteemed panelist of scientists, researchers, and practitioners, led by our moderator, Dr. Boryan Law. Dr. Law received his PhD in material science and engineering from Stanford University, and for the past 3 decades has been involved in R&D projects related to electric and hybrid vehicle evaluation and advanced battery diagnostics and prognostics. His major research activities comprise laboratory and real-life battery and vehicle testing, data collection and analysis, battery modeling and simulation, battery performance and life prediction, and battery fast charging technology development. Currently, he is a Directorate Fellow in the Energy and Environmental Science and Technology Group at the Idaho National Laboratory. And if that wasn't enough, he's also a member of the PRiME Organizing Committee. So with cred like that, it's very easy to see why we have asked him to moderate our discussion today. So please join me in welcoming Dr. Boryan Law to the virtual stage at this time. Dr. Law, the floor is yours, sir.
Thank you, Chris. It's my great pleasure to be the moderator today. I think we have very good program today. We have 3 very distinguished speakers that are going to be on the panel. Each one of them going to present their perspective about the future electrification of transportation. And then at the end of the presentation, we're going to have some Q&A. We hope to have a very live dialogues about how we're going to foresee the pathway to the future electrification so we can change the world and change the society toward a more greener and more sustainable future. So I would like to welcome everyone here and also our speakers, and hopefully we will have a chance to have a very good discussion later on in the Q&A sessions. So the first speaker we have is Hidetaka Nishikori. Hidetaka is the a program manager for Japanese new battery research project Rising 2. He will be introduced later as we come into his presentation. He's now in the New Energy and Industrial Technology Development Organization. The acronym is NEDO in Japan. And his talk, I think, going to be very inspiring about how the future solid-state battery going to impact the transportation electrification aspect. Our next speaker is Chang Hwan Kim. Dr. Kim going to talk about the journey toward a sustainable mobility, electrification. He's from Hyundai Motor Company in Korea. I think his experience with the fuel cell as well as battery powered electric vehicle, it's going to be very intriguing to hear his perspective about the electrification in the broader reach of the Korean community to the world and global market. The next speaker is Sunita Satyapal. Sunita is heading the U.S. Department of Energy Hydrogen and Fuel Cell Technology Office. Sunita going to give a very in-depth perspectives about how the DOE looking into the future in terms of the hydrogen infrastructure and the fuel cell technology that might be fueled another new driving force for the electrification of the transportation. So we're looking forward to hear her talk as well. With that, I think I'm going to go on the introduction for the first speaker. Mr. Hidetaka Nishikori is a very seasoned researcher. He completed his master's degree at the Tokyo Institute of Technology in 1998. He joined Toyota Motor Corporation in 1998, that year. During his initial year in Toyota, Dr. Nishikori worked on fuel cell R&D, such as metal hydrides, electrodes, and electrochemical catalysis, before moving into biofuel cell research over the next few years in the early 2000s. After undertaking the research management of advanced batteries, primarily in the metal air area, he moved into management of a national project, Rising 2, in 2016. So this is an interesting assignment for him from industry to a government entity, NEDO. And it's an advanced project to develop innovative batteries for future EV. So let's welcome Dr. Nishikori to give his presentation today.
Sorry. Thank you for moderator. I'm Hidetaka Nishikori, belonging to NEDO. I really appreciate every effort of all staffs handling this summit. And it's my honor to be invited to this summit. Today, I would like to talk about R&D activities of next generation batteries in national projects of NEDO. These contents of my presentation. First, I will talk about an overview of NEDO. There are two missions of us. One is to address energy and global environmental problems. Another is to enhance industrial technology. On the lower, our positioning is shown. We propose technologies or strategies to national government and Ministry of Economy, Trade and Industry. After that, we get national budgets. And we propose grant design of R&D activities to industries or universities or public research institutes. So we fund R&D budget to participants of R&D activities. So next, I will introduce future direction of automotive batteries. These are trends in automotive OEMs. As you know, in recent years, the concept of mass or case, they are having attracting attention. And the battery, that batteries are key technologies. In addition, we think high-performance electrical vehicles will enrich these concepts. Therefore, the demand on high-performance battery, it has been growing. On the upper, requirements to high-performance battery are shown. Of course, each requirement is important. Besides, we think the compatibility of several requirements necessary. On the lower, long-term forecast of the technology and the market is shown. We guess from the middle of 2020s, the proportion of all solid-state LIVs will increase. And from the 2030s, the proportion of innovative batteries will increase. Please let me introduce our ongoing battery R&D projects. We have two main projects and sub-projects. One of main projects is solid EV for all solid-state batteries. Another is Rising 2 project for innovative batteries. From now on, I will talk about solid EV project. Before the explanation of the project itself, I will introduce our recognition or expectation on all solid-state LIVs. In organic solid electrolytes have several advantages. For example, non-flammable, thermal stability, chemical stability, and so on. We think these advantages enhance energy density or power of battery pack. These are expectations for all solid-state LIVs. First, from the viewpoint of battery cell, we think high voltage stability important because it will not only contribute to enhance the capacity, but also the additional high voltage will enhance the energy density. Next, from the viewpoint of module and battery pack, we think high temperature stability important because it will contribute to reduce the auxiliary units of battery pack, such as blower or exhaust duct and so on. In consequence, from the battery system viewpoint, we expect all solid-state LIVs much lighter and much smaller than ordinary ones. So let me go back to 3DB project. Mission of 3DB project is to create a common architecture for commercializing all solid-state LIVs EV applications. It is not only a material activity, but also, for example, structure, battery structure or battery manufacturing process, and so on. Next, performance targets during mass production. There are three targets. One is 600 watt-hour per liter. next $90 per kilowatt hour, and 10 minutes quick charging time. This is the framework of research and management. The project leader is Yasuo Ishiguro, belonging to Libtech. 24 private corporations, 4 public research institutes, and universities, they are participating in this project. There are various kinds of participants. We have 2 groups. One is Consortium for Lithium-Ion Battery Technology and Evaluation Center, referred to as Libtech. It is in industrial perspective. Another is a university and research institute. It is in scientific perspective. So please let me introduce our baseline cells. At the starting point of this project, the structure of battery was monolayer, and the manufacturing process was batch process. And its energy density was 160 watt per liter. We have 2 kinds of generations. In first generation baseline cell, the target is set 450 watt per liter. And in this first generation, the battery structure or manufacturing process are emphasized. In next generation baseline cell, the target is set as 800 watt per liter. In this next generation, developments of materials are emphasized. I will introduce outcomes in first generation. We saw the agglomeration of materials or voids between materials. They are important issues. So we try to improve mixing process or dispersion media. For example, to optimize dispersion force, we tried several kinds of mixing methods. In consequence, loading ratio of active materials increased more than 35% successfully. And the energy density of battery cell increased more than twice. From now on, I will talk about Rising 2 project. There are 3 missions of Rising 2. First is to clarify basic principles and mechanisms of battery reaction. Second is to improve reliability and performance of battery. In detail, innovative batteries that we call. Third is to create new battery community. The target of this project is to demonstrate innovative battery having a specific energy of 500 watt per kilogram, which will lead us to realize EV's driving range of 500 kilometers or more by 2030. This is a framework of research and management. Project leader is Professor Dr. Takeshi Abe in Kyoto University. 10 private corporations, 3 public research institutes, and 21 universities are participating in this project. We have two kinds of intensive research base. Kyoto University research base is responsible for batteries driven by anion. In detail, Fluoride Shuttle battery group and zinc battery group. AIST research base is responsible for batteries driven by lithium Cation. In detail, combustion battery group and sulfide battery group. So from now on, I will show example outcomes of innovative batteries. First, Fluoride Shuttle battery. On the left, the specification of battery is shown. Positive active material is copper, was copper, and negative aluminum fluoride, electrolyte barium F2 based one. We succeeded in confirming 100 watt per kilogram specific energy, being the world top level. Meanwhile, we analyzed fluoride ion distribution in electrolytes by neutron beam diffraction. We found out fluoride ion conductivity path in electrolyte. Of course, this outcome will contribute to the R&D of superior electrolyte. Next, zinc battery. As you can see, we confirmed 312 watt per kilogram specific energy successfully with our handmade 8 ampere hour cell. Meanwhile, we analyzed zinc segregation by cross-sectional X-ray CT scanning images. As you can see, thanks to improvement of electrode, we succeeded in eliminating zinc segregation. Of course, this outcome contributed to a high performance battery cell. On the last slide of Rising 2, I will introduce a Cation shuttle batteries. On the left, combustion cell is shown. Positive active material is fluoride, iron fluoride, and 15 layers electrode was packed in laminate film. We confirmed the 319 watt per kilogram of specific density. It was a world top level. Next, on the right, this lithium MSX cell is shown. Positive active material is vanadium sulfide, and 20 layers electrode packed. As well as a combustion cell, specific energy was 314. It was a successful value. Finally, please let me summarize my talk. We think open R&D platform next generation batteries. This make interconnection of high added value technologies easy and speedy. Of course, we will continue to make every effort to establish such kind of platform. That's all of my presentation. I appreciate your kind attention. Thank you.
Thank you, Dr. Nishikori-san, for a very interesting presentation. I think it's given us a very good overview about the NEDO project for the next generation of batteries, particularly on the solid state battery and metal air or metal based batteries. Could be very interesting as the way we look into the future. And thank you very much. Let's wait for the collection of the questions. I don't see any open question at this point, but I'm sure there are going to be more questions coming up during the other presentations. So we were going to collect all the questions in the panel discussion. So at that time, we'll invite you back to the panel so we can have more cultural discussion about your presentation and other questions that people from the audience might have. So thank you so much. Let's move to the next presentation. The second speaker is Chang Kim. Chang Hwan received his Bachelor in Chemical Engineering degree from Yonsei University. And then he did his graduate study in the United States He got his master's degree in chemical engineering and material science engineering, and the PhD in chemical engineering from the University of Michigan in Ann Arbor in 2005. He currently is in charge of the advanced activities and energy and environmental system research for future mobility at Hyundai Motor Company in Korea. And he's also a vice president for energy and environmental chemical systems laboratory. Prior joining Hyundai in 2014, he started his industry career as a staff researcher at General Motor Global R&D Center in Warren, Michigan. He was leading the low temperature automotive catalysis and lean gasoline after treatment developments. His industrial catalysis experience, including the catalysis deactivation and the catalyst characterization and catalytic reaction kinetics and reaction pathways, catalysts for alternatively fueled vehicles, such as alcohol or natural gas, with advanced combustions for hybrid vehicles. It's very unique experience, I believe. And before joining the automotive industry, he conducted research in hydrogen and fuel cell area as assistant research scientist in the Hydrogen Energy Technology Laboratory at University of Michigan. He has authored over 120 journal publications and several US patents combining for automotive applications. Dr. Kim is the recipient of awards including the US Council for Automotive Research. The acronym is US CAR, Special Recognition Award, and he served as the president of the Michigan Catalyst Society from 2013 to 2014. And he's currently an editorial board member of the Emission Control Science and Technology by Springer. So let's welcome Dr. Kim for his presentation.
Thank you for a great introduction. This is Chang Hwan Kim from Hyundai Motor Company. I'd like to thank the organizing committee, especially to Korean ECS committee members for giving us opportunity to share the HMC perspectives on future mobility through the electrification. Before I start, I would like to mention that I'm subbing for Dr. Taewon Lim, who pioneered and led a lot of core activities in electrifications and fuel cells in Hyundai Motor Company. Fortunately, he couldn't join this morning. So I hope I can deliver some of his message through my presentations. So my talk will cover, what is the urgent and toughest journey towards the sustainable mobility that we are responsible for as automotive manufacturers. And the biggest transition nowadays is electrification. So I probably have to start with the climate change. So all this, the sustainable mobility and electrification of automotive industry is mainly because of the climate change. I know there is still big arguments whether how severe that will be, but we've seen a lot of increase in the extreme events, in wildfires and some of the extreme floodings. And there's a lot of the challenges in urbanizations, and particle noise and CO2 levels are increasing. So among all the challenges, the climate challenge will be generate unprecedented losses of both lives and wealth. So worldwide efforts to protect the nature and overcome this environmental crisis is still ongoing. And 5 years ago, the Paris 2015 was a big initiative to change or mitigate some global climate change. And there was a global agreement on the reduction of climate change and the goal of limiting global warmings to less than 2 degrees Celsius compared to the pre-industrial levels. So with that movement, we are responsible as the auto manufacturers, which generates a lot of CO2 from our products. There is a lot of efforts being made to how to make the CO2 neutral mobility. In fact, in parallel, all the governments around the world have tightened the CO2 emission regulation for new vehicle models, approximately about 4 to 5% each year since 2015. And it's still ongoing, and by 2030 and 2050, all OEMs are targeting to have CO2 free for including manufacturing and all the products on the road. And speaking of the regulations, China and EU has been very aggressive in the CO2 emission regulations, as you can see in this the charts. By 2025, it has to be more than 30–40% reduction from what we have currently. In parallel, there are also a lot of big global movement towards the decarbonization in the 21st century through the renewable energies and green hydrogen. I mean, 2020, a lot of people may remember 2020 as with the COVID-19 pandemic, but if you look at the new energy initiatives from around the world, there are a number of initiatives being published. For example, the Korea, right before start of summer, Korean government plans to produce the 6.2 million hydrogen cars by 2040 and build 1,200 hydrogen refueling stations by contributing a lot of the government budgets to accelerate the transition. Also, there's a huge strategies being announced in the European side. The German and EU also announced the hydrogen strategy over the summer. And I didn't list it here, but the California also recently announced that they're going to have a strong zero emission requirements for heavy duty trucks. By 2045, they're going to be 100% zero emission trucks in California. So there's a huge regulation side as well as some of the government side. There are a lot of initiatives and regulations is ongoing, and again, we are responsible to respond to meet their targets and the requirements. So it is unavoidable to have a great transition to implement the electrification in our existing conventional ICE engines. So Hyundai's the power sources to lead this transition are 3 separate strategies. Market and customers driven changes are coming really fast. As you could feel, if you go to the dealership, there are a lot of options in the propulsion systems for the same models. The first, still the majority of the vehicles are equipped with the ICE engines. So Hyundai as an OEM, one of the leading OEM manufacturers, we are continuously making efforts to improve the efficiency of ICE engines, and also we are trying to reduce our weight to improve the fuel efficiency and reduce the CO2 emissions. Also, we do hybridization with all different options. We have a mild hybrid technologies and the full hybrid, high voltage hybrid electric vehicles, and also offer the plug-in hybrid electric vehicles in some regions. Ultimately, the full electrifications can be achieved via the two separate pathways. As you can see, the 100% clean mobility can be achieved from the battery electric and the fuel cell electric vehicles. Having said that, the electrification of Hyundai Kia vehicles has been quite aggressive among the leading OEMs. For the first part of the 2020, if you look at the volume of the EV sales from both Hyundai and Kia combined, we sold more than 50,000 units for the first 5 months of 2020, which is right behind of the Tesla. And further, we have announced this year that we are going to have a dedicated EV brand called the Ioniq. We have Ioniq 5 and 6, 7 product line in the pipeline, and then bring to all 3 all-electric vehicles to market over the next 4 years. And all the EV, the battery electric vehicles will be equipped with the designated platform we call eGMP platform that has the fast charging and longer the range features in the field with the advanced technology. So speaking of the advanced technology in the battery electric vehicle, battery will be a key technology. Our previous speaker kind of introduced a lot of advancement in the battery side. But at the same time, the EV market is growing so rapidly. So there is a need for advanced battery technology is also growing. And the market is been projecting more than 50 million vehicles of the EV by 2035. And if you look at the amount of the gigawatt unit, if you look at the 10 or 20 million units for the batteries required for the level of volume, it's about 1 terawatt hour of the battery amount. So that's a big significant increase in the battery, and also that is going to be driven by some of the cost, and also the volume, and the manufacturer and all raw materials are related to achieve those targets. Speaking of the battery, the costs, we already kind of have optimized in the manufacturing costs, and materials are fixed to meet the industry requirements for the long range, the battery packs. And at the same time, the cost parity is quite important for the battery electric vehicle penetrations for the customer level. The price of the battery has gone down quite a bit, and hopefully with this kind of the economies of the scale, the price will go down further, but it already leveled off at the about $100 level per the kilowatt hour range. So there still the breakthrough is required in terms of the range and durability and charging time and safety and performance. In the previous talk, there are a lot of trends in the battery technology, but we do see that some of the large two areas in the beyond the current lithium-ion battery to improve the cost and energy density and safety. Solid state battery was well introduced in the previous talk, so I'm not going to go details, but lithium metal battery also has some the good features with the high energy density, which can achieve close up to 1,000 watt-hour per liter. And also it can utilize the existing LIB manufacturing facility to ease the implementation of this technology than other technologies. So there are a lot of, I know there are a lot of programs from the government funded, for example, DOE, the Battery 500, A lot of university and national labs are working on the lithium metal battery and lithium metal anode technologies. And there are a lot of activities in the NEDO, as we learned earlier. The solid state battery is making a big advancements as well. So as OEM, as a smart user, to be a smart user, we are looking close into how the battery industry will move for the next generation batteries. For the case of the fuel cell electric vehicle, the Hyundai, as most of you know, is the first mass producing OEM for the world first fuel cell electric vehicles in 2013. And we recently released our second generation Nexo with a 99% of localization of the parts. And we have several products in the pipeline for the passenger car side, but also we expanded our application to the buses and heavy-duty trucks. We already deployed the city bus with the several the fuel cell the packs being used for the current Nexus system. Also, we expanded our portfolio to the heavy-duty trucks, and you may have seen in the July that we have shipped more than 10 the fuel cell electric trucks to Switzerland to look at how our performance of the trucks with the PM fuel cell will perform, and then we will supply more than 1,000 trucks by the 2025. And further, we expanded our portfolio to the non-automotive businesses. For example, the hydrogen ships, trains, and the urban air mobility application, and also some of the generator applications for the mobile generator applications for the EVs. Speaking of the technology, for next generation fuel cell, we'll share a lot of parts from the battery electric vehicles. The biggest challenges for in performance will be the PM fuel cell stack, as well as some of the hydrogen storage. But the fuel cell catalyst technology is one of the biggest challenge to reduce the cost, and the success of the low platinum PEM fuel cell depends on the development of the highly active durable catalyst. And we're also making a lot of efforts to improve our next generation fuel cell technology. As you can see, I'm not going to go over details, as you have seen a lot of these charts. You know, we for decades ago, most of the industry being deploying or implementing the commercial level of the fuel cell stack using the platinum only catalyst, but now it's moving towards the bimetallic platinum alloy with the core shell and some intermetallic. There are a lot of approaches, but we are to implement in the commercial application, we are making the extra steps further to get the performance and also require durability. So if you look at in the right hand side, our recent advancement in the fuel cell catalyst, showing the very structurally well-defined order nanoparticles and with excellent oxygen reduction reactivity and the durability. So we are targeting the greater than some of the DOE targets been defined for the last 10 years. All these technology in battery electric vehicles and the fuel cell electric vehicles, another the components, elements that we are also focusing is how we can improve the sustainability. Many of you probably heard that battery electric vehicle is not the CO2 free. It's not because of the energy they get from the charging station, but also the energy required to manufacture the batteries. I probably have to walk you through from this slide. From the battery electric vehicles, compared to the IC, it doesn't have the tailpipe CO2 emission, as you can see here, from you typically see from IC engines. So you significantly reduce the CO2 level. However, all the electricity that they need to run the battery electric vehicles is not CO2 free, as all different countries has different energy generation portfolio. For example, Norway is making electricity out of renewables, so it doesn't produce much CO2 at all. But still, you see the significant of the amount of CO2 because manufacturing would still require a lot of CO2 emissions. And typically, the current battery production is the green. Its amount can be as much as 50% of the total manufacturing of CO2 emissions. And if you look at the different models in the battery electric vehicles, each one has a different CO2 footprint. As you can see, even for the similar amount of the battery pack size here, where you can produce those battery packs will differentiate different CO2 footprint. So it is very important that the development of the low carbon footprint battery technologies for the future sustainable mobility. For the case of the hydrogen, as you may be familiar with the hydrogen currently in the worldwide is generated from some fuel reforming process, and it's called gray hydrogen. It emits more than 13 kilograms of CO2 per 1 kilogram of hydrogen. But there are a lot of movements and initiatives. I'm sure that Sunita is going to introduce a lot of initiatives in the green hydrogen production. But through the electrochemical process, electrolysis, combined with some renewable energy from the winds or solar energy, we probably can have a CO2-free hydrogens directly into our fuel cell vehicles. And also, it may take a little time to really meet the very low cost of hydrogens, but blue hydrogen is also alternative options that the CO2, combining with the CO2, we can significantly reduce the CO2 level per the 1 kilogram of hydrogen productions through the SMR per CO2, and also we have some combined steam and CO2 reforming. So the automotive industry, to wrap this our perspective up, the automotive industry is in great transition toward the electrifications for the next 5-10 years. The future dedicated EV platforms will be equipped with a lighter, smaller, safer, and cheaper batteries optimized for flexible capacity and performance. And continuous efforts to develop better fuel cell catalyst technology is crucial for a larger and faster penetration of fuel cell electric vehicles. And the journey of the sustainable mobility will ultimately require how to minimize the carbon footprint in the electrification for automotive industry. And as a leading automotive industry, engine, fuel cell, battery, and fuel cell electric, all the full portfolio, we will try to have the sustainable mobility. In fact, the HMG has announced that as a first mover in the forthcoming hydrogen economy, we will invest $6.3 billion in hydrogen economy by 2030. So there are a lot of things together in academia, industry, and also national labs. So I will wrap up my talk, and thank you very much for your attention.
Thank you, Dr. Kim. I think it's a very informative talk, and also very to the point. I think that the last few slides are talking about the carbon neutral aspect, not just for the battery or fuel cell operation, but the overall energy intensity and the materials intensity in terms of the production is certainly as an aspect that we haven't discussed very much. So I appreciate that aspect very much. Thank you. Now we're going to move to the third presentation by Sunita Satyapal. I would like to introduce Sunita, who is the director of the U.S. Department of Energy's Hydrogen and Fuel Cell Technology Office within the Office of Energy Efficiency and Renewable Energy. She is responsible for overall strategy and execution of hydrogen and fuel cell research activities, including oversight and coordination of about $150 million a year of research, development, demonstration programs. She also the current chair of the International Partnership for Hydrogen and Fuel Cell in the Economy, a government partnership coordinating hydrogen activity across over 20 countries, and the European Commission. Prior to joining DOE in 2003, she was with the United Technology in Connecticut, serving as a visiting assistant professor at Vassar College and a visiting student at Hokkaido University. In addition to hydrogen and fuel cell R&D, she has worked in the area of laser diagnostics in photo dissociation and the combustion of chemical warfare agents and various energy-related technologies. She received her PhD in physical chemistry from Columbia University, and she also did her postdoc work in applied and engineering physics at Cornell University. She has numerous publications and has 10 patents issued. I'm sure she received a lot of recognition, including a presidential rank award. So that's welcome, Sunita, and she's going to talk about her programs in the hydrogen and fuel cell technology area.
Thank you. So thank you, Marianne, and thank you to the ECS as well for the invitation and the great presentations just before. So I'll start with global perspectives. And this is really a very exciting time for hydrogen and fuel cells. For the first time, the industry surpassed 1 gigawatt in terms of fuel cell shipments worldwide just last year. You can see transport. We heard from Chang, some of the big drivers. We see big growth there. I think we expect to see a lot more with trucks and some of the larger vehicles. And we also see a big increase in electrolysis. So 25-fold increase in electrolyzer deployments, less than a megawatt about a decade ago. And then we also see, these are the latest statistics, about 25,000 fuel cell cars doubled in sales just in 1 year, and almost 500 fueling stations. So again, a lot of progress worldwide. So what's going on in the US? Here, this gives you a snapshot of where we are. We have thousands of fuel cells, commercial fuel cells in the US. 35,000 forklifts. Most people don't know this niche market industry, but we have major companies now, Amazon, Walmart, Home Depot, that are using hydrogen fuel cell forklifts inside their warehouses, completely zero emissions, millions of fuelings. In fact, every few seconds, some customer is fueling hydrogen with a fuel cell forklift. Buses just starting to increase, about 45 stations, mostly in California, and about 145 if we include the stations that are used for the forklift industry. And quite a few cars, still the most, of course, Korea and others are really ramping up. But right now it's still more than any other country. And many of you probably saw the big announcement from the governor in California just last week for a 100% ban on the sale of internal combustion engine, passenger cars and light trucks. For drivers, a zero emission vehicle mandate. And then we have quite a lot of hydrogen. So we produce about 10 million metric tons of hydrogen in the US. That's about 1/7 of the global supply. Quite a bit of pipeline and caverns. So 3 underground geological storage caverns for hydrogen, including the world's largest in Texas, and then plans by many of the states for hydrogen stations. And one of the key points really is that you can produce hydrogen from diverse domestic resources. So again, hydrogen's part of all of the portfolio. Chang mentioned gray hydrogen, the main focus. We have multiple offices at DOE. Our Office of Fossil Energy is focusing on natural gas, coal gasification. This is not gray, but blue hydrogen, so with CCUS. Of course, you can use biomass, waste, and then water splitting, which is where we're focusing, electrolysis, direct photoelectrochemical production, really multiple ways of producing hydrogen, which brings me to what we call our H2 at scale initiative at DOE. How do we basically tie in large scale production of hydrogen as well as storage and then utilization of hydrogen across multiple end use sectors? So today what we have, all we know is the conventional grid here in orange, the large natural gas infrastructure that we have. But if we could produce hydrogen, again, through any of these resources, either from electricity or even directly, that opens up many possibilities. So you can either feed that back to the grid instead of just conventional conventional storage, or once you produce that hydrogen, you can use it for multiple end-use applications. So not just cars, but transportation in general, hydrogen plus CO2 to synthetic fuels. We have a growing program in that area. Most of the hydrogen today is used for oil refining, fertilizer production, steel, and other applications, heating. So really the value is the fact that you can provide benefits across sectors and across applications. And so we've done quite a bit of analysis. And I mentioned today we produced 10 million metric tons, but our national labs, NREL, has shown that we could get basically 2 to 4 times more economically viable hydrogen production and demand. And so the strategy here is really threefold. Scaling up the technologies in key sectors, so especially those that are hard to decarbonize, like heavy duty trucks. The second is continue to the R&D. So we still need to reduce cost, improve performance. We'll talk about this. And then finally, the third is what I call enablers. So harmonizing codes and standards, safety. We started some workforce development projects. So really everything that's necessary for a sustainable market. So these are the areas that we're working on. And if you look at our office mission, again, it's the applied office. We're focusing on 3 main areas. So fuel cells, components, catalysts, as well as systems, focusing on heavy duty applications. Hydrogen, which includes production, delivery, storage, again, cost, a lot of R&D here. And then what we call systems development and integration. How do we accelerate that technology, integrate, for instance, electrolyzers with the grid, look at hybrid systems. And in all of these areas, we have very specific targets, specific goals on what's needed to be competitive. So basically, I think most of you are familiar with the DOE targets. It was great to hear Chang saying some of these targets maybe we have to make even more aggressive. Usually people complain about the DOE targets, but this gives you an idea of where we need to be. Again, we have many more targets. These are high-level targets in each of the key areas. So I'll talk a little bit about these. And most people ask about the budget, so I do have one slide on the budget. So we have in fiscal year 2020, our new fiscal year just started. We don't have a budget yet, but looks like we're at roughly about 150 million. The breakout here shows you, again, strong support for fuel cells, hydrogen, this new systems development integration. So really cover very comprehensive view of everything that's needed to scale up hydrogen, starting from the R&D, early stage R&D, all the way up to demonstration. So I'll talk about some of the newest activities. And the key here is really how do we get to scale? So we've done quite a bit of analysis. So looking across the country, where would the hydrogen come from? Solar, wind, the green is nuclear, different demand scenarios where, for instance, the red shows where local demand would exceed supply. But the idea is really if you could co-locate production, large-scale production next to multiple end uses, that can help to drive down cost. And so for the first time, we have some large-scale projects in the US that we're supporting. Again, the key is getting up to scale. So we start around the megawatt scale, eventually larger. And so Texas, Florida, the Midwest with nuclear, and then some new projects with marine and data centers, and looking at demand. So this shows you, various example scenarios of where that hydrogen could be used for, again, different applications. So in Texas, new project looking at wind, solar, renewable natural gas, waste, producing hydrogen and then using it for different end-use applications. Florida, solar to hydrogen. This is 1 megawatt with an electrolyzer, storing it, using it for light-duty truck fleet. And then another one with nuclear. For the first time, we'll have 2 nuclear to hydrogen projects and using that hydrogen on site. Also just announced last month a new marine project in California. For those of you in San Francisco, this will be a floating barge, barge that will have an electrolyzer and a fuel cell. And this is the first passenger ferry in the Western Hemisphere. Hydrogen, 150 passengers will be fueling that with the hydrogen, completely zero emissions, and have a fuel cell to charge a battery electric vessel. First large-scale data center project. We're happy that Microsoft will also be involved in this one in Utah. And then steel production. Steel actually accounts for about 8% of total greenhouse gas emissions worldwide. And so instead of using coal, we use hydrogen. Again, you mine iron ore and you reduce that iron oxide to iron. Using hydrogen, green hydrogen, can get you substantial emissions reduction. So we have 2 projects on that as well. So the next I'll talk about is cost. And so as you know, we have a lot of targets. The green shows the DOE targets. These are application specific. And every year we assess based on the state of the art technology, where are we compared to those targets? And if we project to high volume, high manufacturing volumes, and then at low volumes, for instance, we have the newest number here, 165, based on commercial fuel cell cars at 3,000 units per year. And then you see storage tanks, still carbon fiber. Cost of hydrogen, if you go to a fueling station, a commercial fueling station with your credit card, can still be very high in terms of the price that you pay. So again, we're focusing on how do we reduce cost. And I'll show just 2 examples. One is electrolysis. Since there are a lot of questions here today, if you go to basically get a PEM electrolyzer, ranges as high as about $1,500 a kilowatt. And industry consensus shows that we could get at volumes down to about 400. And so if we do, and we can get to about 3 cents a kilowatt hour and get full utilization, because the key is really not only to use the electrolyzer during intermittent solar or wind, but full utilization here, you can get to less than $2 a kilogram. But today, even at low volume, our levelized cost analysis shows hydrogen at $5 to $6 per kilogram, even at 5 to 7 cents a kilowatt hour at high utilization. So I think we're getting there, lots of progress. And so we do a lot more detailed analysis. Where do we need to reduce the cost? For instance, electrolysis, hydrogen storage tanks, carbon fiber is a big piece of the cost. So we have projects there. And then for stations, for instance, these keep changing, but you can see compressors, storage dispensers, still a lot of cost drivers. And then on the fuel cell side, again, these are constantly being updated, but this gives you a snapshot of where we are In terms of power density, looks very good. I think we're hearing reports even higher, actually. Specific power, not bad. And this is just stack cost, stack durability, especially for heavy duty trucks, is going to be key. And then this shows you again, if we project to very high volumes, and you can actually buy these components at high volumes at scale, where we still have cost issues in terms of the technology. So catalyst still ends up being dominant. But you have many other components here, GDLs and so forth, that are contributing to the cost that need to be looked at. And so we do have a number of targets. Instead of 8,000 hours for light duty, we're going to 25,000, 30,000 hours. So these Class 8 long-haul trucks require 1 million miles in terms of commercial viability for the life of the vehicle. And then, as Chang mentioned, it's really important to look at efficiency. And so life cycle analysis, for the first time looking at heavy duty, different types of vehicles, the diesel example versus the scenarios with clean hydrogen. So we'll continue to do that. And I want to end really with the really important message here, which is the importance of collaboration. And I love this quote here. This is a very technical audience, and we really appreciate all of your work. We think about all the progress in batteries and fuel cells. It's really due to many of you. But we really need to expand the playing field, and information, outreach, education is so critical. So I wanted to highlight just a few examples. IPHE, which was formed in 2003, coordinates across 20 countries, the European Commission, really addressing a lot of the challenges for hydrogen fuel cells. We have a number of other collaborations as well. And just announced early career chapter for IPHE. So if there are any students, postdocs, early career professionals, go to iphe.net. We have students and again, members joining from around the world. And then the Center for Hydrogen Safety. Safety is also critical. So here too, we have many companies, universities can join, share information, resources, training materials, lots of good information available. So I wanted to end again in the spirit of information. Feel free to go to our website. We have monthly webinars, increase your H2 IQ and so forth. And hopefully most of the ECS members will remember that October 8th is National Hydrogen and Fuel Cells Day. So hydrogen, the most abundant element in the universe, 3/4 of the known universe is hydrogen. Number 1 in the periodic table, 1.008, so 10.8. Congress, believe it or not, 6th year in a row, passed the resolution, and it is National Hydrogen Day. You may remember 3 years ago, I was just telling John and Chris, we had the event when we had our previous boss and Nobel Prize winner, Steve Chu, who came to the ECS for his plenary in a fuel cell vehicle. And ECS also had the great ride and drive as well. So I think the key message is to help spread the word about hydrogen, about fuel cells, about all of these new technologies. So with that, I'll end. Thank you.
Thank you, Sunita. It's a very good overview. I think we certainly get a very up-to-date information about the hydrogen technology and the fuel cell improvements in terms of the electrification for the transportation application. I think, again, we finally come to the point with the 3 presentations. We begin to collect quite a few questions now. I think, Sunita, because you just finished your talk, so I'm sure your question gonna coming up with time. That's at this point, transition to the panel discussion. We roughly at about 20 minutes, so I think maybe before we answer some of the key questions from the audience, I think from the 3 talks, I can summarize there's there was a very interesting pathway for us to look at the electrification. One is the battery pathway, the other one is hydrogen-based fuel cell pathway. At the end, we are using electrons as the currency for the energy conversion and the energy storage application. But I think the hydrogen and the battery certainly has a different storage mechanism, and the associated infrastructure, the production cost, and the logistics all has very different types of requirements. Overall, I think that the whole supply chain issues still need to be solved out. In my view from the three presentations, I think a battery, looking at all kinds of possibilities in terms of how they store the electrons. You know, you have all kinds of chemistries that we discussed today, from solid state to the liquids, from aqueous to the a different kind of electrolytes. My question is, if we look at the Tesla as a benchmark, Tesla taking almost 18 years to get to where they are today. They have been sticking with one principle, which is you got to have the scale in order to reduce the cost, and in order to continue to improve the technology and provide a reasonable market share in terms of how to entice people buying electric vehicle. They haven't changed the chemistry of the battery very much. They have been continuing to use this a system integration as the tool to reduce their costs in terms of manufacturing. On the other hand, I see more and more company involved in the battery research, from lithium-based to zinc and many other type of battery chemistries. But we don't look at the scale, so I wonder how this is going to prevail in terms of reducing the cost for the overall production of vehicles that can sustain the electrification. I think this question probably more for Dr. Kim, because from OEM's perspective, this probably is more of a concern than the government policies and R&D directions.
I agree. I think the cost really matters for electrification, as you mentioned, and the battery electric, especially, the battery cost is the kind of a key component. And as you mentioned, the Tesla, I think there's still room as we can cut a little bit of cost by the economies of scale. As the raw materials is fixed and the manufacturing costs facility is kind of it has not been changed much, but I will say this, Brian. So the first phase, I mean, you mentioned the 18 months. I mean, the Tesla started, and all the EV manufacturers, including the existing OEMs. The focal point for the first at the early phase was how we can secure the minimum range, because range anxiety was always the kind of the greater concern before. But now, no one hears range anxiety anymore, right? It's just cost. So nowadays it's kind of matter of cost, and the battery electric vehicle will be driven by the battery cost. As we do work on the advanced battery technologies, it is very important to have a better energy density or energy, the safety, and also some of the fast charging or some great features. But those are all for some next generation. But right now, the most important for the customer point of view and the industry point of view, the cost is going to be very critical, and it's going to go down. And the Tesla, as they announced, they're going to still utilize their the volume and scale to reduce further. And also the chemistry side, as you mentioned, I mean, they kind of have a pretty smart move in the China for low cost battery packs. They claim that the LFP is another options they're going to take for the low cost, low range, the battery packs. So there are all mixed strategies that all the OEMs is going to take, whether there's going to be small passenger cars or it's SUVs or it's going to be the heavy duty. So that's the cost will be a very important part.
Thank you. Thank you for your comment. I think it's good that we hear from the OEM's perspective. I think I'm going to also direct the question to Nishikori. Nishikori, I think in Japan, you know, from your presentation, we understand a lot of interesting in the technology development to advance the possibility of battery technology in supporting the transition. But we haven't heard very much about the philosophical side, how Japanese industry and the government begin to look into the electrification issues in the more global scale, not just for domestic issues, but for competing with the global scale. How Japan is looking into this kind of issues in terms of the supply chain?
Oh, all right. I think in NEDO, we think the battery high performance battery will be contributed to enhance the strength of Japanese battery industry. All right. So now we are making effort to develop, for example, all-solid batteries and innovative batteries. At the starting point of NEDO, our mission is for next generation batteries. Therefore, we think the development and next generation batteries will be a key point of next of Japan battery industry in Japan. Of course, at this moment, from now on, we think, for example, manufacturing process and so on will be important. Therefore, we will not only development of material, but also, for example, simplifies manufacturing process of batteries. It will be more important from now on. That's
Thank you. Thank you for your comments. Sunita, because I kind of mentioned the battery technology, but I believe in the hydrogen and fuel cell counterpart, the whole supply chain issue, as you discussed in the hydrogen at scale, certainly try to address the issue from the source of hydrogen all the way to the distribution and the fuel cell technology. We haven't really talked about a lot of recycling as much as in the battery technology. But Tesla certainly driving the electric vehicle to a bright light that the electrification seems to be an acceptable pathway for the society. How do you see that? I'm not trying to put you in a competitive mode, but I'm more interested is how do you see the hydrogen and fuel cell actually could become viable as well as the way or an alternative to the current electric vehicle drive into the future of transportation?
Thank you, Florian. And it's really not, I think it's really important to emphasize it's not either or batteries, or fuel cells. It's not the competition. I think we really need all of them. I mean, when you think about, it's and I keep saying that, now it's 2020, And for me, like the year 2000 was not that long ago. You know, just 20 years went by so fast. In 20 years, it'll be 2040. You know, we keep saying it's such a long time, but we need, you know, all the technologies. The market penetration is so slow. And so I think, you know, in certain, especially when you have short driving range, you know, a lot of stop and go traffic, you don't need, you know, a lot of charging. The larger vehicles will, where it's hard to electrify with a battery, or if you need, you know, very fast fueling, like with the heavy duty trucks, long driving range. I think there are many, many examples where I think more industry and all the stakeholders are recognizing that you need both. And so, you know, again, I think there's a lot of progress with both. Definitely on the infrastructure side, that's again the whole purpose of the H2S scale vision is that we can help scale up quickly the production, the hydrogen piece, and then the infrastructure. And so if we can use some of these, you know, large scale applications, that will help drive down the cost. Again, enable that whole infrastructure. Again, we used hydrogen before. It's been very widely used, you know, decades ago. We you know, trade 100 million tons of hydrogen, and we're seeing, you know, so much interest, especially with, you know, all the stimulus funding, with the shipping from Australia to Japan, you know, so many countries. So I think it's, you know, it's definitely there. We see, because of the low cost of renewables, there's even more interest. The energy storage play, we have, for the first time, we're connecting a fast charger with our national labs with an electrolyzer, because the electrolyzer can also help compensate. The dynamic response is very good, so it can also offer grid services. So again, it's many different attributes of the hydrogen H2S scale vision can provide benefits.
I fully agree. I think that this is definitely a very interesting aspect of the electrification. Is, you know, there's no well-defined pathway, and we all try to find the road to the future. Maybe what you need is another Elon Musk that can take the hydrogen and fuel cell technology to the new pathway, and that will create the fancy market driving force to push that technology. I don't think, you know, without Tesla, the EV can come to this point in the marketplace. So I think that's a very interesting aspect. Worthwhile to consider, not just the technology, but also we need to have the right business model to promote the acceptance of the new technology into our society. So I appreciate your comments. I think we have a few minutes, and there's some more technical questions. I think we need to provide the opportunity for the audience to involve. I know there's a few questions for Nishikori about the cyclability of the new battery chemistries, particularly with the zinc air chemistry. I think that the zinc is notorious for their dendrite growth and the recyclability issues.
Yeah.
Do you have any comments in how the Rising 2 or the other solid state approach can solve this problem?
Thank you. So I would like to answer in a zinc air battery. How to reduce the zinc dendrite? For example, we have tried some options, for example, additives and so on. So unfortunately, I can't answer the cyclability quantitatively. However, combined with analytical technology, our cyclability of our battery has been improved drastically. That's my answer. Thank you.
Okay. Is the cyclability also an issue for the solid state battery today?
Yeah, of course.
All right, well, thank you. Thank you for your answer. For Dr. Kim, I think Sunita touched the basis, talking about should we support both the market between battery powered electric vehicle and fuel cell powered electric vehicle, or should we divide them in the market sector? I think we have some consensus already, but it's a question for you. So what's your comment on that?
I definitely in the same page with this, Sunita, that it's gonna be no one way or the other. We definitely have to have a both in parallel, and market penetration is again mainly driven from some of the infrastructure and also the cost of the fuels. And the as an OEM, we are focusing to reduce the cost so that we can have a better price, or take the burden out of our customer side. But total cost of ownership side, definitely it's going to be. The electricity is a lot cheaper than hydrogen fuel. But if the hydrogen infrastructure and the cost and price will be reached, eventually, definitely, both will be also part of it. And also, we have the fuel cell on board for generating electricity, but the hydrogen can be also eventually, or in the long run, can be utilized to generate the electricity in the power plant. So that can also, become the good energy source for battery electric. So I think they're going to be all associated together.
Good. Thank you so much. I think it's important to look at a broader picture, not just the technology.
Yes.
And their own supply chain. I think the overall balance of energy and distribution and the resource is all very critical. So we cannot discriminate one technology versus the other just because the technical aspect.
Exactly.
The other question I see from the audience is that we're talking about infrastructure, the fast charging infrastructure. Does Hyundai has any strategy that is interesting that to be shared with this audience?
Well, definitely we have engineering requirement for design the battery modules. How the C rates wise and some performance wise. But the infrastructure wise, there's a limited kind of control over to it, right? So there will be some different kind of, Tesla, that's why Tesla had made their own way to invest on their fast charger charging stations. But as Hyundai, as a global manufacturers, we are kind of making some all different strategies to be more viable for the customer needs, as well as some of the product needs. So there'll be some different approaches that we are taking, and we are open and trying to be very versatile to in that the charging wise. So, but definitely we are our vehicles will be capable of handling the fast charging for sure. But as the technology moves up, we will have to see what is most viable way of doing it. How I can answer. Yeah.
Yeah. I think we can also go back to the supply chain issues for three of you. I think for Dr. Kim, what's the perspective on the reuse, repurposing, and also recycling of
I
the
think
battery?
that's a great question. I think the recycling is kind of one of the one of the areas that all the battery industry is being looking into. It has not been fixed, although there is a lot of reuse recycling initiatives But I think the key is how we can define the state of the health of the used batteries. And of course, the recycling side, I know there are a lot of chemical companies already have their own process to recycling, but I think that right now the penetration of EV has not enough to have enough volume to really form a good size of the industry in the recycling in the material side. But for reuse of the batteries, definitely there are a lot of other challenges or technologies that we have to really make it more viable and solid to get the more values, the accurate values of the recycled the batteries. So still, I think it's ongoing, and Hyundai is very active in doing in terms of ESS, as well as some of the some other applications for reusable recycling. So that's kind of what I can answer for their questions.
All right, thank you. I think I will have the same question to Nishikori. Does Japan has any focus right now on the recycling, reuse, or repurposing of battery in the research portfolio?
Oh, so unfortunately, our department does not handle the issue of recycling. However, my view is the importance is how to use easy material element. For easy material element means, for example, iron or aluminum and so on. I think how to utilize such kind of materials. If we can apply such kind of material to the battery, this recycling of batteries will be made more easier. It's my personal view. Thank you.
Good, thank you. Sunita, I think you probably had the last chance. Does hydrogen technology and fuel cell has recycling issues as well?
Well, I think, in general, especially with platinum, most companies will look at recycling that platinum. So I think it's very similar to others, but I see Chris there, so I think it's almost the end of the session. So I'll keep my answer short.
All right, thank you. Okay. So I think we pretty much run out of time, so I'll hand the whole session back to Chris. And I thank the three very distinguished speakers today to share their experience. Thank you so much.
Thank you all. That was a wonderful session. And I think that is about all the time we have for this. So I would ask everybody in the crowd to join me in thanking our moderator, Borean Liao, for leading this wonderful discussion. And a very special thanks to our speakers, Hidetaka Nishikori, Chang Kim, and Sunita Satyapal for sharing their knowledge and insight with all of us today. I would like to again thank SK Innovation and all of our general meeting sponsors for their generous support. And also, along with a sincere thanks to our many symposia sponsors shown here who make the cutting edge technical sessions like E2S a reality. You can find more information about our sponsors and exhibitors in our digital exhibitor and vendor guide, available at electrochem.org/dev2020. And also, just a reminder, we invite you to join us tomorrow evening in the US, Thursday morning in Asia, as we proudly present The Legends of Battery Science, a celebration with Nobel laureates M. Stanley Whittingham and Akira Yoshino. This event will feature talks from Professor Whittingham and Dr. Yoshino, as well as a live panel discussion with Q&A. You can submit questions for Stan and Akira through ECS's social media posts on Facebook, LinkedIn, Twitter, and Instagram, so be sure to check that out. And finally, we will end the week with the ECS Awards and Recognition Ceremony on Thursday evening in the US, Friday morning in Asia. Thanks again to Borian Liao for moderating our distinguished panel, and to Hidetaka Nishikori, Chang Hwan Kim, and Sunita Satyapal for being with us today. And with that, I wish you good day, good night, and we'll be seeing you all week long during PRiME 2020. Thanks, everybody. Have a great day. Bye-bye.